Hi, this is the Science Chef. Today we'll be learning about the first law of electrolysis. Go nowhere, and we'll be right back after this timeout. In an introductory tutorial of electrolysis, we learned that electrolysis is a chemical decomposition of an ionic compound by passing direct current through its molten state or aqueous solution. This decomposition leads to the deposition of metals or liberation of gases at the various electrodes. To learn more about the basic concepts of electrolysis, check the link in the description. According to Michael Faraday, the first law of electrolysis states that the mass m of an element deposited at the electrode during electrolysis is directly proportional to the quantity of electricity Q passed through the electrolyte. Mathematically, it is expressed as m directly proportional to Q, where m is the mass of elements deposited in grams and Q is the quantity of electricity passed in coulombs. If we remove the sign of proportionality, the equation becomes m equals to Zq, where Z is the electrochemical equivalence of the element. A plot of m against Q gives us a straight line graph passing through the origin with its slope equal to the electrochemical equivalence of the elements in question. But the quantity of electricity is given as the product of current in amperes and time in seconds. Therefore, substituting this into equation 2, we have m equals Zit. Usually, Z is assumed to have a unitary value in chemistry, as it's always not used in the electrolysis calculations. This implies that equation 4 will become mass equals to the product of current and time. And a plot of mass m against time t gives us a straight line graph passing through the origin, whose slope is equal to the current I flowing through the electrolyte. We have modified the first law of electrolysis to suit gases. Thus, the volume V of a gas liberated at the electrodes during electrolysis is directly proportional to the quantity of electricity Q passed through the electrolyte, and the equation can also be modified thus: V equals IT. Electrolysis, being a redox process, involves the transfer of electrons from the anode to the cathode. The quantity of electricity required to discharge 1 mole of electrons at the electrodes during electrolysis is known as a Faraday and has a value of 96,500 coulombs per mole. For univalent cations like sodium and potassium ions, 1 Faraday is needed to deposit 1 mole of the metals at the cathode during electrolysis. For divalent cations like calcium, magnesium and copper 2 ions, 2 Faradays are needed to deposit 1 mole of the metals at the cathode, because for this to happen, 2 moles of electrons must be gained by their ions. Similarly, for trivalent cations like aluminium ion, 3 Faradays are needed to deposit 1 mole of the metal during electrolysis. However, for univalent non-metallic cation like hydrogen, 2 Faradays are required to liberate 1 mole of the gas at the cathode during electrolysis, because hydrogen gas is a diatomic molecule. Similarly, for univalent anions like the chloride, bromide and iodide ions, 2 Faradays are required to liberate 1 mole of their gases during electrolysis because they are diatomic molecules. For divalent anions like the oxide ion, 4 Faradays are required to liberate 1 mole of oxygen gas at the anode during electrolysis because it is a diatomic molecule, and for each atom to be formed, 2 moles of electrons must be lost. Similarly, for a univalent anion like the hydroxide ion, 4 Faradays are required to liberate 1 mole of oxygen gas. To learn more on this, watch our tutorial on the factors affecting the preferential discharge of ions at the electrodes during electrolysis. The link is in the description. Before we solve some problems on the first law of electrolysis, let's look at some formulae that we will be applying. The first is the formula used for calculating the mass of elements deposited at the electrodes during electrolysis, and is given as m over ar equals to q over nf equals it over nf, where m is the mass of the element deposited A is the relative atomic mass of the element, Q is the quantity of electricity passed, I is the current flowing through the electrolyte in amperes, T is the time of current flow in seconds, N is the number of moles of electrons lost or gained by the ion of the element in its oxidation or reduction half equation, and F is the Faraday's constant of 96,500 coulombs per mole. The second formula is a modification of the first and is used for calculating the volume of a gas liberated during electrolysis and is given as V over Vm equals to Q over Nf equals IT over Nf, where V is the volume of the gas liberated, Vm is the molar gas volume at STP with a value of 22.4 dm³. Note that this formula will also be applied in the second law of electrolysis. So it's now time to solve some examples on the Faraday's first law of electrolysis. Example 1. Calculate the number of Faradays or number of moles of electrons that are required to form the following during electrolysis. A. 2 moles of chlorine molecule. B. 2 moles of zinc atoms. C. Half mole of aluminium atom. To solve this question, first of all, we write the half equations for each element and then apply the mole concept. So in example 1a, the oxidation half equation for chlorine is given as shown on the screen. From the equation, we can see that 1 mole of electron needs to be lost by each of the 2 chloride ions to liberate 1 mole of chlorine molecule. And this requires 2 Faradays. Therefore, to liberate 2 moles of chlorine molecules, we need 4 Faradays. Similarly, in example 1b, being a cation, the reduction half equation of zinc is given thus. From the equation, 2 moles of electrons are to be gained by the zinc ion to deposit 1 mole of zinc atom, and this also requires 2 Faradays. Therefore, to deposit 2 moles of zinc atoms, we will need 4 Faradays. Lastly, in example 1c, also being a cation, the reduction half equation of aluminium is as shown on the screen. From the equation, an aluminium ion will gain 3 moles of electrons to deposit 1 mole of aluminium atom, and this requires 3 Faradays. Therefore, to deposit 0.5 moles of aluminium atoms, we will need 3 times 0.5 Faradays, and that will give us 1.5 Faradays. Example 2. Calculate the quantity of electricity required to deposit or liberate each of the following. A. 5.6 dm³ of oxygen gas at STP. B. 2.7 grams of aluminium. C. 44,800 cm³ of hydrogen gas at STP. Just like example 1, to solve these problems, we will write the half equations and then apply the mole concept. So in example 2a, the oxidation half equation for oxygen is as stated on the screen. We will assume that the oxygen gas was liberated from the electrolysis of a molten oxide, hence this equation. From this equation, 2 moles of oxide ions will have to lose 2 moles of electrons each, making a total of 4 moles of electrons to liberate 1 mole of oxygen gas. But 1 mole of oxygen gas occupies 22.4 dm³ at STP, and 1 Faraday is equivalent to 96,500 coulombs per mole. This implies that 4 times 96,500 coulombs will be required to liberate 22.4 dm³ of oxygen at STP. Therefore, to liberate 5.6 dm³, we will require 96,500 coulombs of electricity. Similarly, in example 2b, the reduction half equation for aluminium is given thus. From this equation, 3 Faradays are required to deposit 1 mole of aluminium. But 1 mole of aluminium weighs 27 grams. This means that 3 times 96,500 coulombs of electricity are required to deposit 27 grams of aluminium. Therefore, to deposit 2.7 grams of aluminium, we require 28,950 coulombs of electricity. Lastly, in example 2c, 2 moles of hydrogen ions will need to gain 1 mole of electron each to liberate 1 mole of hydrogen gas at STP. But 1 mole of every gas occupies 22.4 dm cube, which is equivalent to 22,400 cm cube at STP. Hence, 2 times 96,500 coulombs of electricity will be required to liberate 24,400 cm cube of hydrogen gas at STP. So, to liberate 44,800 cm cube of hydrogen gas at STP, we will need 386,000 coulombs of electricity. Example 3. Calculate the amount of current that must flow for 2.5 hours through a solution of copper 2 sulfate to deposit 0.1 grams of copper. Take the relative atomic mass of copper to be 64 and Faraday's constant as 96,500 coulombs per mole. As always, the first thing we are expected to do is to write out the cathodic half equation of copper to iron. From this, we will see that the number of moles of electrons N required to deposit 1 mole of copper is 2. But we are given the mass of copper deposited, the time of current flow, the relative atomic mass of copper, and the Faraday's constant, and asked to find the amount of current that must flow through the solution for that specified time. So we convert the given time to seconds, which is 9,000 seconds. Then use the equation that links all the parameters together. Make I the subject of formula, substitute the values, and evaluate to obtain 0.0335 amperes as the answer. Example 4. For how long must a current of 0.4 amperes needs to flow through a solution of nickel 2 chloride to deposit 0.2 grams of nickel? Take the relative atomic mass of nickel as 59 and Faraday's constant as 96,500 coulombs per mole. Here we are given the amount of current, mass of nickel deposited, the relative atomic mass of nickel, Faraday's constant, and asked to determine the time it will take the current to flow. Before we proceed, we must write the reduction half equation for nickel 2 ion to know the number of moles of electrons gained, which is 2. Next, we use the equation that links all the parameters together. Make T subject of formula, substitute the values, and evaluate to obtain 1,308.47 seconds, or approximately 21.8 minutes. Example 5. Calculate the volume of gas liberated at the anode at STP when 48,250 coulombs of electricity is passed through a aqueous sodium chloride solution. Volume occupied by 1 mole of gas at STP equals 22.4 dm cube. Faraday's constant equals 96,500 coulombs per mole. In this question, we are given the quantity of electricity, the molar gas volume, and the Faraday's constant, and asked to calculate the volume of gas that was liberated at STP by that quantity of electricity. Since it is the dilute solution of sodium chloride that is being electrolyzed, the gas that will be liberated at the anode is oxygen. To learn why oxygen would be liberated at the anode instead of chlorine, you need to watch that tutorial on the factors affecting the preferential discharge of ions at the electrodes during electrolysis. So from the anodic half equation of oxygen, the number of moles of electrons lost by the hydroxide ions to form a molecule of oxygen gas is 4. So using the equation that links all the parameters together, making V subject of formula, substituting and evaluating, we obtain 2.8 dm cube as the volume of oxygen gas that was liberated at STP. In our next tutorial, we're looking at the Faraday's second law of electrolysis. If you'd like to be notified when the video is published, subscribe to our channel and turn on the notification bell. Remain on top till I see you when I'll see you.